All right, section 11.3, we're going to continue operations on vectors. Now, if you'll remember in section 11.2 and 1, actually, we talked about adding and subtracting vectors. We talked about scalar multiples of vectors. The thing we didn't talk about is what you do to multiply vectors, right? We didn't talk about that. So sections 3 and 4 are going to address what multiplication means in vector calculus, okay, what we're doing. And so in particular, one of the types of multiplication is called the dot product. The one we're going to encounter in 11.4 is called the cross product, okay? So the dot product actually takes two vectors and it gives you a scalar when you're done. So if you have a vector u1, u2, vector u that's u1, u2, and a vector v that's v1, v2, then the dot product is the multiplication of the individual components, and then we add them together. It's the same if you do it in 3 dimensions. You just multiply the 3 different components component-wise and add them together. So you start with vectors on a dot product and you end with scalars. Okay? We're going to see something completely different happen in section 11.4 when we do cross products. But for dot products, this is what it looks like. And it looks like that multiplication dot that you've been using since somewhere about, maybe ninth grade at the latest, somewhere in there. You start using dots instead of, x's for multiplication to clear it up and make sure that you're not using x's for a variable and x's for multiplication. So it's the same dot that's used there. There's a lot of properties for dot products. Did everybody get this one? Okay. So there's 5 in particular that are listed in theorem 11.4. These are properties of the dot product. So if you have vectors u, v, and w and scalar c, then the dot product's commutative. That's the first one. U times v is v times u. Okay, u dot v is v dot u. It's also distributive. If you have a dot product across the addition of vectors, it's the same as doing the dot product with each one of them individually and then adding them together. Okay, so I can distribute the dot product. The third one says that if there's a scalar multiple of the dot product, you could actually do the scalar on the first vector and then do dot product with the second. Or you could do the scalar multiple on the second vector and it can dot product with the first. Or you can do the dot product first and the scalar last. These are all interchangeable. So there's sort of some associativity kind of thing going on here where I can shift the c, the scalar c, and it doesn't change the value of the dot product. Number 4 is like an identity kind of a property, right? So when I or a zero property, I should say it that way. The zero property for multiplication looks a lot like this with our whole numbers and real numbers and so forth. But if you take the zero vector and it's a dot product, there should be a dot in here, that's missing, I apologize. A zero vector with a dot product with v, you get 0. And that should make sense, right? You're just multiplying 0 by each of the components, you're going to get 0 when it's all done. And the last one actually talks about what happens when you do a dot product of something with itself. So when you do the dot product of a vector with itself, you get its magnitude squared. And if you think about what magnitude is, that should make sense. Magnitude is, I'll actually write it down here. And we'll do it with just 2 components, would be the square root of u1 times, I don't want to use the dot because I'm using it indifferently here. I will use a parenthesis. u1 times u1 plus u2 times u2, all right? Or we would have written, another way we've written it is like u1 squared. Maybe that's a little bit better for what we're looking at now. And it's u2 squared. And then if you take the square of this, right, you end up just getting u1 squared plus u2 squared. But that's the same thing as u1 plus u2. All right, so we can see that this is going to actually work sort of as expected. Okay, so the magnitude squared is the same as the dot product of a vector with itself. And so just like back in section 1 and in section 2 when we ended with 3 dimensions, we're going to do several of these different kinds of things as an example. So A says u dot v, B says u dot u, C says the magnitude of u squared, D has the dot product of u and v times the vector v, And then we have the vector u dot with the 2 times the vector v. Okay, so we're going to do all of these pieces. I am given 3-dimensional vectors here. They are written in component form, not the IJK form like we've seen before, so I'll keep them in component form for the sake of just simplicity. Okay, so the first one that we're supposed to do is u dot v. So feel free to not write everything down. I mean, I get that, but just in case you look back and you're like, I don't remember what she did on that, I want to have it written down in my notes, okay? So we're going to multiply them component-wise. So this is the first component of u times the first component of v, plus the second component of u times the second component of v, plus the third component of u times the third component of v. We're going to multiply, we're going to add. Let's see, we have 0 minus 2 minus 12, which gives me what? Negative 14. Okay, is that good? All right. Now, the second one said u dot u. So u dot u would be taking each of the vector components of u multiplied by themselves. So this is 2 times 2 plus negative 1 times negative 1 plus 3 times 3. Or feel free to write squared on each of those, the same thing, of course. So I have 4 plus 1 plus 9, which is what? Positive 14. Now, 14 is not the only answer we'll be getting. It is sheer happenstance that these two match except for the sign. That's not a, like, oh my goodness, is there a pattern going on? There's not. It's just what they happen to be, okay? And then C says that we're going to take the magnitude of u and we're going to square it. I think that's what it was. Is that right? Yeah, the magnitude of u squared. Now, if you happen to notice, this is something we already established over here in our properties. What is the magnitude of u squared? It's just u dot u, right? But didn't we just do that? We did. So don't recreate the wheel. By that theorem, this is u dot u. And we already did that. It's 14. So let's just write it down instead of actually doing it again. D is a little interesting. It's actually going to give us a non-scalar. We're going to get a vector when we're done. So it's u dot v, and then it's multiplied by v. And notice there isn't a dot in between. Now, the reason there isn't a dot in between is because u dot v is not a vector. U dot v is a scalar. What is it? Negative 14. It's the first thing that we did. So this first piece is actually negative 14. And now I've got negative 14 times, right, a scalar times the vector v, and I will just multiply each of the components of v for that to happen. So the first one is multiplying by 0, that's 0. The next one's negative 28. And the last one's 56. At least it is if my notes are right. Does that work? Good. And our last one, E, is u dot 2v. Now, we can do this. You can multiply 2 times v and then multiply that times the other one. But there's an easier way to do this problem. So we have a property over here that talks about sort of some associativity of how I can move scalars around, right? That's the third one that's on here, the ability to sort of shift the C into different locations. If I shift the 2 to the beginning, which I'm allowed to do by that property, it says I'm going to get the same thing, then I have the u dot v together, and I know what u dot v is, right? So we're going to use that property to our advantage. I will actually write down the shift that I'm making, but then u dot v is negative 14 times that 2, so I have negative 28. Does that make sense? Now, if you didn't happen to see this, or if we hadn't already done u dot v, and you did it right where it was, you're still going to get negative 28, right? We would just be multiplying 2 times the vector v. We would end up getting 0, 4, negative 8, and then we do a dot product of that with vector u. I'll get negative 28, okay? But if I happen to notice a property that I can use, then we might as well use it. All good? Okay. So the next thing that we're going to see, usableness, if you will, for dot products is going to come in finding the angle that happens between two non-zero vectors. So if we have an angle theta between two non-zero vectors u and v, and theta is between 0 and pi, then the cosine of theta is u dot v divided by the product of the magnitude of u and the magnitude of v. And this will give me an angle measure in radians. Calculus is always in radians, right? Now that's a given. But this will be measuring the angle, well, the cosine of the angle, and then we can find the angle if necessary between vectors u and v. Okay? So using that formula, we're going to be given a vector, two vectors, excuse me. And in part A, it actually is going to ask us to do it in radians. That's how this is going to be designed, right? The problem is used in radians. Then we're going to turn it in degrees at the end. Okay, so we're going to just remind ourselves how it's done. All right, so our vector is, vector for u, three-dimensional, is I plus 3j minus 2k. And vector v is 2i minus 3k. What's vector v missing? It's missing a j. So what is the coefficient of the j?
0.
It's 0. Okay, so I'm mentioning it here. I think you probably would have caught that already, but just to make it real clear, we do not have a two-dimensional vector. I mean, we do, but we can write it in a three-dimensional way so that it can interact properly with the other three-dimensional vector that we have. Okay? All right, so the first thing we're going to do, well, let me write down their formula. This is the cosine of theta is u dot v over the magnitude of u times the magnitude of v. Now, you can do this all in one fell swoop if you would like. That's fine. I'm not going to. I'm going to find the three pieces, and then I'm going to put it all back in. Okay, so this is kind of like this piece of it anyway. I'm sort of thinking back to those of you who did Calc 1 with me where we did the four-step method for the limit process instead of doing it all at one time. It's just two different ways of thinking about it. If you weren't in Calc 1 with me, just ignore that. Don't worry about it. But we're going to find together u dot v, and we're going to find the magnitude of u, and we're going to find the magnitude of v. Okay? So u dot v means I multiply component-wise. And so I am going to multiply the coefficients. The I, the j, the k doesn't matter here. So I have, and I'll write it down again, I've got 1 times 2 plus 3 times 0 plus, it'll be minus 2 times negative 3. Did I get those right? I think so. Okay, so do some quick addition, subtract, or addition and multiplication. What do we got going on? What do we have? We have 8. Excellent. That's my numerator. So when I come back up here in a minute, in fact, I'll write it in right now, 8 is in my numerator. Now we're going to do the magnitude of u. So the magnitude of u is found by taking the square root of each of these components squared. So I have 1 squared plus 3 squared plus, and if you want to write negative 2 squared, you can, but it's the same thing as writing 2 squared, so I'm going to drop the negative since I'm squaring it anyway. 1 squared, so I have 1 plus 9 plus 4. That gives me 14. 14 is the popular number for the day, isn't it? So I have square root 14 here. Okay. And then we have v squared. Now, one of the components for v is 0. Write it or don't write it, it doesn't really matter. But the other components, the non-zero ones, matter. So I have 2 squared plus 3 squared. So that's 4, and 9 gives me the square root of what? That one's 13, square root of 13. So up in our problem, I have square root of 14, and I have square root of 13. So I'm going to just box this in to remind you where we are, not because it's the finalization, but because I'm now moving back up here, okay? And I'm going to make the part that's at the bottom small so that it's kind of able to be shifted and not in our way, so that we can finish working with the part at the top. Man, that's what I did for getting it too close. Let's try it one more time. Okay, not going to get quite everything. I did. Good. Okay, shift it over to the side. There's our work. All right, so taking a look then at here, I will have the cosine of theta of kind of a mess, right? It's 8 over, and square root of 14 times square root of 13. You can simplify what the square root of 14 and 13 are by multiplying the 14 and 13 if you want. But we're not stopping there anyway. The goal is to find theta. So what am I going to have to do to find theta when I know the cosine of theta? Inverse cosine. So I will take the inverse cosine of 8 over, what is 14 times 13? Somebody do it? Maybe I did it on my paper. 182? Excellent. All right, so take your calculator, find the inverse cosine value of 8 over the square root of 182. It starts in radians. Mine's in degrees because I was using it for trig, so I'm going to change that. Okay, I have it now. What did you guys get for theta in radians? It doesn't tell us how many decimals to round to or anything, so let's go with, I've got 3 written down on my paper, so let's go with 3. What did you get, Preston?
In radians or degrees?
Yep, let's go with radians first.
Change this up. I got 0.936.
Okay, did everybody get 0.936 for radians? Excellent. Now, somebody else tell me for degrees, what did you get? 53.6. And remember, your calculator will just change it to degrees for you if you want. You can also take this value in radians and you can multiply it by 180 over pi. And that'll change it into degrees as well. It's another option. So either way, those are our 2 values that we've got here. And just pay attention to whatever it tells you on the rounding rules. I didn't write anything into this problem, so we're sort of being a little bit arbitrary here. But in general, they usually tell you. So, okay. New vocabulary word that you've probably heard in physics, or if you haven't, you will shortly. Orthogonal. Have you heard the word orthogonal before? Oh, all right, you will. Okay, so vectors are considered orthogonal when their dot product is 0. So orthogonal is like perpendicular. We use it in 2 dimensions interchangeably. It's used a little bit different in 3 dimensions, but we're going to figure out if they are orthogonal by whether or not their dot product is 0. Now, processing through that definition and like mathematically is really straightforward, right? I can decide if something's orthogonal simply by finding the dot product. And if it's 0, they're orthogonal. And if it's not, they aren't, right? So this question asks us if they're orthogonal, which we will address that. It also asks us if they're parallel, which is another option. It asks us if they were neither. So we can start with either checking the parallel or checking the orthogonal. If you happen to notice that they're parallel, you can just go with that and not check the orthogonal, right? Or if you happen to find that they're orthogonal, you don't really need to check the parallel. These are not parallel. Do you remember how we decide if they're parallel? Scalar multiples of each other. What's the red flag telling you from the real get-go that these are not scalar multiples of each other? The signs are all messed up, right? So one of them has only positive signs and one of them has a positive and a negative. There's no way there's going to be a scalar multiple between them. So we definitely know that it is not parallel. And to be honest, that's usually the easiest one to check because you can usually check that visually without having to do any work, especially if there's sign issues, okay? So this is not parallel because I'm going to say they are not scalar multiples. So let's check the dot product, okay? So we're going to do u dot v, and this will check for us if they're orthogonal. So if I do 2 times 2 plus negative 1 times 4, what happens? It's 0. So they're orthogonal, right? That's how easy it is to process that, right? They're orthogonal to one another. So why do we use the word orthogonal instead of the word perpendicular? Well,
It's fun.
because it's fun. Well, maybe. There's several reasons. We'll explore them a little bit later. But it does have the idea of forming right angles. That part's the same thing, okay? So we are creating a right angle with these two. This is what's telling us that if they've got dot products of 0. There is a right angle formed by these vectors. All right, definition. We're going to let u and v be non-zero vectors. U is going to be W1, W2, so it's a composition, right? It's an addition, I should say, or a sum of 2 vectors, W and W2. W1 and W2 are parallel, and W2 is orthogonal to V. W, the one that's orthogonal, no, I think there's something missing there. Maybe it's on your paper. I've got something missing. There's a component down there, but I can't think, I think it's W2. I'm pretty sure. No, it's W1 because it's listed later. This should say W1. Please fix that. W1 is called the projection of U onto V, or the vector component of U along V. It's denoted by W1 equals projection, and you see a lower subscript V on vector U. And I'll draw you a sketch of this in a second so you have an idea of what they're talking about. W2 is U minus W1, which that should make sense. If you just take this and rewrite it, you can get this, right? And it's called the vector component of U that's orthogonal to V. Okay, so we do this all the time in a very special case. So I'm going to draw you the special case, and then I'm going to extend it to the picture that's more happening in general here. And I'm going to draw it in 2 dimensions because I don't do so well in 3 dimensions, and as evidenced with you guys on the boards last time, most of you do not either. Okay, so here's the one you've seen before, and you've never heard this language. When you draw a vector or a line, we'll do it as a vector because we're working in vectors. So when you draw a vector in 2 dimensions, if you were to shine a flashlight on top of the vector down, it would create a shadow below, right? Or if you were to shine a flashlight on the side of it on the y-axis, and you were to shine the flashlight this way or back this way, I guess it would be this way from your direction, it would create a shadow along the y-axis. And what happens is it actually creates a triangle, and that's how we usually draw it, is that we draw this triangle like this, right? There's a triangle drawn right here. And we call this the y value and this the x value, and we write it as an ordered pair xy, right? This is the ordered pair xy. It corresponds to the height and the width. This idea of taking this slanted vector, the pink one, and pushing it down and looking at how far across it is along the x-axis or how far up and down it is on the y-axis is a projection. Okay, like the projection for the projector, right? It's actually fleshing out how far over in this direction is it and how far up. We do this all the time when we're looking in trig, right, at finding angles and things like that. But what this is actually telling you is that you can do this in any case. So if I were to take a random vector in space, here's my orange one, and I wanted to project it down onto another vector, we'll make this funny color here, over here, right? This is not an x, this is not a y, but I could still drop a perpendicular down here on top of this. And I could talk about this distance, and I could talk about this distance. Are you with me? That's what these are. These vector components and this projection component are these 2 kind of green distances. They're projecting it down onto this kind of yellowish vector that's on the bottom. Okay? So it doesn't have to be done in a perpendicular way to the x and the y-axis. It can be done onto any other space. So if you can imagine somebody standing, let's use a shape that you're familiar with, at least you should be. Are you familiar with the Leaning Tower of Pisa? Right, so it's not vertical, straight up and down, right? It's got a slant to it. You can use anything slanted if you want. So a lot of these telephone poles, when we had our tornado, they started slanting, right? The light poles were slanting. So anything that's slanted already. If you were to have the sun directly above and it came down, it would cast a shadow of a certain length onto the ground, correct? Now there's actually a height of that telephone pole or whatever as well, because it's no longer reaching as high as it once did if it's now slanted. Yeah? It's not, right? If I lean like this, my height went down vertically, correct? That's what happens to your telephone pole, and that's what happens to the Leaning Tower of Pisa, is that it's at a slant anymore. We can talk about how far across the ground it is, and we can talk about how high it really extends up. That's a projection. Okay? So we're going to take, I think there's one more definition, is there? Yeah. Projection theorem, it's on my page before. The projection using dot product. So here's how we find the projection. So if U and V are non-zero vectors, then the projection of U onto V, okay, so it says projection of the vector U, the V is the subscript, is U dot V over the magnitude of V squared, that's going to be a scalar, times the vector V. And then I will get a vector when I'm done. So this piece right here is a scalar. And when I multiply the scalar times the vector, I will end up with a vector. Whoa, whoa, whoa. of a vector when I'm finished. Okay, so this projection vector is a vector. And if you think over here, you can see that this is these green pieces. I end up with this green vector here, and I end up with this green vector here, depending on how I'm projecting. Okay? Okay, so let's do one. Three-dimensional, so I'm definitely not drawing it. We have the projection of vector u, which is 2, negative 1, 3. Vector v, which is 1, 2, 2. We're going to find the projection of u onto v. That's the first one, part A. And then b is the vector component of u orthogonal to v. So I haven't done either of these yet. And in fact, this last one didn't even really describe how to do the vector component, but it did over here. This is how you get the vector component. It's the second step of this. So they are both there. They're just kind of in different places. Okay, so we're going to start with finding this vector component. So let me actually write them down, what we're looking for. We're going to find the projection of u onto v, and previous slide told us, your page as well, that this is, I'm going to write it the exact same way, u dot v over the magnitude of v squared, and then I'm going to multiply all that by vector v. So kind of like the last time, we're going to do this in steps. This is u dot v, and then I'm going to do the magnitude of v squared, and then I'll put those in and multiply them. So u dot v, so I'm going to have 2 times 1 minus 1 times, I don't want to interchange my dots because they mean something different now. Let's use parentheses. 2 times 1 minus 1 times 2 plus 3 times 2. That'll be our dot product. What does that give me? Somebody said it? 6, yes. The vector v magnitude squared is the same thing as doing the dot product of v with itself. Or you can do the magnitude and leave off the square root. That's the same thing. So I have 1 squared plus 2 squared plus 2 squared, which is what? Um, 9. Should be 9.
Oh, yeah.
Yeah? Okay. And there's no square roots because we're taking it, squaring it. So we're either eliminating the square roots or you're saying that we don't need the square root to begin with because we're doing a dot product. Either of those visions, we're still getting a 9, not a square root there on that one. So up here, now I'm going to have that this projection vector, actually let me pull it down here, is equal to 6 over 9 times vector v. So 6 over 9, we can simplify that. That's 2/3, right? And then times vector v, and vector v is 1, 2, 2. So I end up getting what? 2/3, 4/3, 4/3? That look okay? Okay, so this is what we called W1 on the previous definition, like two spots back. This is W1. So this is part A. Finding part B actually takes and finds W2. W2 is the vector u minus the vector that's the component, the projection component W1. So I'll write it in. My u is 2, negative 1, 3. And I'm going to subtract 2/3, 4/3, 4/3 as a vector. You can use your calculator if you need to support with the decimal or the fractions, but it's subtracting component-wise. So I need 2 minus 2/3. What will that give me? 4/3. This is going to give me a vector. I have negative 1 minus plus 4/3. Sorry, minus. It's negative in the middle here, so the minus. So negative 1 minus 4/3 is negative 7/3, right? And then I have 3 minus 4/3. What's that one going to give me? 5/3. 5/3. Yeah, somebody said it. So I'm subtracting component-wise. If it helps you, you're welcome to distribute the -3 before you do it and then do addition. Sometimes it's easier for us to think about that instead of doing those two operations all together. That'd be fine. This one would be the W2, which is the vector component of U orthogonal to V. All right, what do you think? Excellent.